This is the first time that we broadcast both onto YouTube and Twitch at the same time. That seemed to work. Let's check a sound and everything. Yeah, the resolution is pretty good. This video brought to you by not really, it's just the ad that is targeting me. We're also doing X just because. We'll start in a second. Start a new chat. Ah, yeah. So hello. Yeah, we haven't started yet. Hey, give me a second. Okay, I might be maxing out on my upload. Because, ooh, actually can go higher. Going up to 6. So we're not encoding, we're sending the same thing. So when I talk, it's doing that. It keeps oscillating. I don't think it's actually legit. Okay, close that. Just fingers crossed. Okay, I'll start in a sec. Yeah, we have this stream. Still loading the preview. Just on LinkedIn, posting about the stream just in the hope someone joins in. It's having trouble. It's having trouble with this link. Right, now it's on. Okay, we'll pause this. We normally remove this post after the stream is finished. Okay, so I'm doing fuzzy logic today. This tool at the bottom of Bionichaos.com page that doesn't work quite yet. Yeah, I'll start in a second. So we're on Twitch and YouTube, that's great. That's the first time we are doing it, so bear with me. Right, so start developing in a second. Just close that. So we're using Visual Studio Code. We have that running. It's working okay. We're doing a Flask application. Continue developing. So we're doing another live stream development real time. Making a Flask application using Visual Studio Code. This will eventually go onto Bionichaos.com. Are you ready? Yep. Okay, I'll be sharing the code with you that we developed during a previous session.
Great. I'm here to help with code review. Let's see what you've got. This index, HTML for the fuzzy logic waveform detector, is well structured and clear. A few observations. Meta tags, good use of meta tags for SEO and social sharing. CSS and JS linking, you're linking to both a local style.css and a/styles.css. Ensure these aren't conflicting. Also, consider combining the two less than script greater than tags for script, JS into one. Navigation paths, double check the navigation paths like href equals /dot /quote dot. They might need standardization, href equals /quote closing parenthesis dot. Use of external libraries, you're using chart, JS and potentially Plotly, commented out. Just make sure they're not redundant if both are included. Content and structure, the content is informative and well laid out. The use of headers and paragraphs enhances readability. Overall, it's a solid foundation. I'll review the upcoming code for more specific feedback. Your JavaScript code for fetching and displaying EEG data looks efficient and effective. Here are some specific points. Fetch EEG data function, nicely implemented asynchronous function with proper error handling. The check for array content is a good practice. Canvas resizing, adjusting the canvas width based on data length is thoughtful, but ensure it fits well within UE. Chart initialization, good use of chart, JS. Destroying the existing chart before creating a new one is a clean approach. Data mapping and scales, mapping the data points and adjusting the sampling rate is key for accurate representation. The dynamic scaling of the y-axis based on max data point is excellent. Chart options. The responsive and aspect ratio settings are important for different screen sizes. Customizing the title and legend enhances readability. Error handling in display EEG data. Consider adding error handling in case the data processing or chart generation fails. Potential for refactoring. If your application will have more charts, consider creating a generalized chart function to avoid repetition. Performance. If the dataset is very large, monitor performance, especially with canvas resizing and chart rendering. You're doing a great job so far. Let's see the next part of the code. Your Flask backend code for the EEG data analysis application is well organized and seems to cover key functionalities effectively. Here are my observations. Fuzzy logic implementation. The setup for fuzzy variables, membership functions, and rules is well executed. It should provide a robust analysis of EEG data based on amplitude and frequency. Signal processing functions, butter_bandpass and butter_bandpass_filter functions for bandpass filtering are properly implemented. This is crucial for EEG data preprocessing. EEG data generation and preprocessing. Generate_synthetic_EEG is an innovative way to simulate EEG data. The addition of EMG artifacts is thoughtful. Preprocess_EEG_ data does a good job at normalizing the data and extracting amplitude and frequency features. The root is correctly set to render the index, HTML. Generate_EEG for fetching EEG data seems to handle exceptions well. Analyze_EEG, handling post requests, properly processes the EEG data and utilizes the fuzzy logic for analysis. Error handling, good use of try-except blocks to handle exceptions and return appropriate responses. Validation, ensure there is sufficient validation for the incoming data in the analyze_EEG route. Logging, consider adding logging for better debugging and monitoring. Configuration, if not already done, ensure sensitive Based on the code snippets you've shared so far, it seems the result of the fuzzy logic detection, the artifact_risk, is being calculated on the Flask backend and then sent back as a JSON response to a post request made to the analyze_EEG endpoint. However, the front-end part that handles the display of this result in the user interface, UI, has not been shown in the provided code. To display the fuzzy logic detection result, artifact_risk, on your website, you would typically follow these steps. Front-end request. Initiate a post request from your JavaScript front-end to the analyze_EEG endpoint, sending the EEG data for analysis. Backend. Based on the code snippets you've shared so far, it seems the result of the fuzzy logic detection, the artifact_risk, is being calculated on the Flask backend and then sent back as a JSON response to a post request made to the analyze_EEG endpoint. However, the front-end part that handles the display of this result in the user interface, UI, has not been shown in the provided code. Front-end request. Initiate a post request from your JavaScript front-end to the analyze_eg endpoint, sending the EEG data for analysis. Back-end processing. Your Flask application receives this data, processes it through the fuzzy logic system, and returns the artifact_risk as part of the JSON response. Front-end display. Once the response is received on the front end, you can extract the artifact_risk value from the response and display it in the UI. This could be in the form of a text display, a graph, or any other visual representation. In this example, display artifact risk is a function that updates the text content of an element with id artifact risk display on your web page to show the calculated risk. The analyze and display EEG function makes the post request and then updates the UI with the result. Yes, based on your Flask backend code, the artifact_risk is calculated from the amplitude and frequency values derived from the EEG data. This artifact_risk is the output that should be displayed on the front end. To display the artifact_risk on your web page, you'll need to modify your HTML code to include an element where this result can be shown. Here's a suggested modification. Add a display element. Include an element in your HTML where the artifact_risk will be displayed. This could be a simple less than div greater than or less than span greater than element. For example, HTML copy code less than div id equals artifact risk display greater than artifact risk, less than span id equals artifact risk value greater than n, a less than, span greater than less than, div greater than. Update JavaScript function. Ensure your JavaScript functions are correctly fetching the EEG data, sending it to the Flask backend, and then updating this new element with the received artifact_risk. The function display artifact risk I provided earlier would update the text content of the element with id artifact risk value. Styling, optional. You might want to add some CSS to style this display element, making it visually clear and consistent with the rest of your site's design. Remember, it's important to ensure that the front end and back end are properly integrated. The front end should correctly send EEG data to the back end, and the back end should process this data and return the artifact_risk, which the front end then displays.
Okay, that didn't work. Artifact display. So we have this ID. Let's check. JavaScript. Risk element. Get element by ID. Didn't say that, did I? Let's do Control Shift C. Body header. It's the display. Artifact risk not available.
Adding artifact risk (NA) to your HTML is a good starting point. This placeholder shows where the artifact risk value will be displayed once it's calculated. Here's an example of how you can integrate it into your HTML. The less than div greater than wraps the label and value for neat organization and styling. The less than label greater than improves accessibility. The less than span greater than with id equals artifact risk value is where the calculated artifact risk will be dynamically inserted by your JavaScript. Make sure your JavaScript fetches the EEG data, sends it to the backend, and updates the artifact risk value span with the response. This way, when your application is running, NA will be replaced with the actual calculated risk.
We might need to do some troubleshooting. Would like to print the artifact risk at the backend. Yep.
To troubleshoot and print the artifact underscore risk value on the backend, you can add a print statement in your Flask route that handles the EEG data analysis. Here's how you can modify the analyze underscore EEG route to include a print statement for logging the artifact underscore risk. In this modification, the line print, f, artifact underscore risk, will output the artifact underscore risk value to the console or terminal where your Flask application is running. This allows you to monitor the calculated risk values in real time as EEG data is processed, which can be very helpful for debugging and verifying the accuracy of your fuzzy logic implementation.
Is this? Wait a sec. I have a problem with script.js. This is a different script.js. Can we update based on folder structure? And no, that's not correct. Wait, no, that's the JavaScript. The problem that we have two of them, well, one. We do this. This should be a task for GitHub Copilot. No, wait. Control Shift C, I always forget. No, that's fine. So we have a script for the overall page. But then the actual... Alright, it's actually called main.js. And it's in a static folder. Chart.js instead of the Plotly. Yeah, might actually not need this. Yeah, main.js, that's the one. Should be working fine. Can't be reached because it's not running to actually run it. I did add the print statement, but it's not printing the artifact risk at all. It seemed not to be calling the analyze EEG route. Yep.
If the analyze_eg route is not being called, and therefore the artifact_risk is not being printed, there could be a few reasons for this issue. Let's troubleshoot. Front-end request check. Ensure that your JavaScript code is correctly making a post request to analyze_eg. Verify the URL, HTTP method, and data format. Request handler in Flask. Confirm that your Flask app has the analyze_eg route correctly set up to handle post requests. Ensure there are no typos in the route URL or method. Network issues. Sometimes, network issues or misconfigured server settings can prevent requests from reaching the server.
Okay. It should just pick up on the issues.
Your JavaScript code looks well structured for handling EEG data fetching, displaying it in a chart, and sending it for analysis to get the artifact risk. However, if the analyze_e route isn't being called, let's troubleshoot. Ensure function call. Check if analyze and display EEG is being called after fetch EEG data. Currently, fetch EEG data is called to load and display data, but there's no indication that analyze and display EEG is being called with the fetched EEG data. You might need to add a call to analyze and display EEG within fetch EEG data after display EEG data. Endpoint URL. Confirm the URL for the fetch request in analyze and display EEG. It should match your Flask route, analyze_EEG. Data format. Ensure that the EEG data format being sent to analyze_.
We're generating EEG. Response okay. Display EEG. Action fetch. Okay, now we get the artifact risk. Okay, this is working better. We get a value for the artifact risk. Now there's still a couple of issues. We would like the artifact risk to be calculated as we scroll through the synthetic EEG data. Yep.
To calculate the artifact risk as you scroll through the synthetic EEG data, you need to modify your front-end JavaScript to trigger the artifact risk analysis at specific intervals or positions within the EEG data. This can be achieved through a combination of event listeners and data processing. Here's a suggested approach. Add a scroll event listener. Attach an event listener to the element that contains the EEG chart or the scrolling element. This listener will trigger when the user scrolls. Determine data segment. Based on the scroll position, determine the segment of the EEG data to analyze. This might involve calculating which part of the data is currently in view or selecting a fixed size window of data around the current scroll position. Analyze data segment. Call the analyze and display EEG function with just the segment of data you've determined needs analysis. Here's a basic implementation outline. Note, the implementation of determined data segment will depend on how you're displaying the EEG data and how you want to segment it for analysis. This could be a non-trivial task, especially if the EEG data is displayed as a continuous waveform and you need to calculate which part of the data corresponds to the current view. Additionally, consider the performance implications. Analyzing EEG data can be computationally intensive, and triggering this process on every scroll event could lead to performance issues. You might want to debounce or throttle the scroll event handler to limit the frequency of analysis calls.
Okay.
Remember to tell
Couple of quick things. We would like the value. I forgot what it's called, the output of the fuzzy logic algorithm, the artifact risk, to be calculated when the mouse is released, so when scrolling is finished. Also, can we make sure on the HTML page below the chart the artifact risk is still showing not available. Can we make sure it's actually displaying the actual value? Yep.
To address your requirements, you'll need to make adjustments to both the JavaScript event handling and the HTML display for the artifact risk. Here's a step-by-step guide. Instead of triggering the artifact risk calculation on every scroll, you should do it when the mouse is released after scrolling. This can be done by listening for the mouse up event. You might also want to consider the touch end event for touch devices. Here's an updated event listener. To ensure that the artifact risk is displayed and updated correctly on your HTML page, you should modify the display artifact risk function to change the content of the relevant HTML element. Assuming your HTML has an element like this, your display artifact risk function should update the artifact risk value element. Debouncing. Depending on the user interaction and data size, you might want to debounce the function attached to the mouse up and touch end events to avoid excessive calculations. Data segment calculation. The logic in determined data segment needs to be carefully implemented to select the correct segment of data for analysis based on the scroll position. Testing. Thoroughly test these changes to ensure they work as expected across different devices and browsers, especially considering touch events. These modifications should address your requirements of calculating and displaying the artifact risk upon the completion of scrolling.
Yeah, get this error. Let's make sure the ID is okay. Oh, that's the class label. It's the same label. Span. And JavaScript. So this is a new code. Have event listeners. No. Do we have elements by ID? Each is scroll container. We have a scroll container? No. Okay, I'll have to adjust quite a few things. Should mute this. I have to remember to unmute it if I wanna do the music again. Yes, there's no music, so it's not distracting. That's good. Okay, the artifact risk still not showing anything. We need to just update. It's really bizarre. Why is it? To update this.
To update the HTML section for displaying the artifact risk, you want to ensure that the artifact risk display is correctly formatted and placed in a suitable location on your page. From your provided code, it seems like you already have the basic setup in place. Here's a refined version for clarity and improved layout. I removed the commented out HTML elements for clarity. Added a margin top style to the artifact risk display div to give some space between the chart and the risk display, enhancing the visual layout. You can adjust this margin as needed for your page's design. The artifact risk display is positioned right after the EEG chart container so that it is prominently displayed below the EEG chart. This structure should make the artifact risk value visible and clearly associated with the EEG chart. Ensure your JavaScript updates the artifact risk value span as needed when new risk values are calculated. The error message type error, artifact risk, to fixed is not a function suggests that artifact risk, the value you're trying to format with to fixed, is not a number. This could happen if the backend is sending a response that does not have the artifact underscore risk as a numerical value, or if there's some issue in how the data is being processed or passed in the front end. Here's how you can troubleshoot and fix this issue. Check backend response. Make sure your Flask backend is returning artifact underscore risk as a numerical value. You can log the output on the backend before sending it to confirm. Inspect front-end data. In your Analyze and Display EEG function, log the result you're receiving from the server to see what it contains. Update the Display Artifact Risk function. Modify this function to handle cases where artifact risk may not be a number. You can use typeof to check the data type. Check data parsing. Ensure that the artifact risk is correctly parsed in the front end. If it's sent as a stringified number, you might need to convert it back to a number using parsefloat. By following these steps, you should be able to identify where the problem lies, in the data type of the artifact underscore risk, and appropriately handle it in your JavaScript code.
There is a value for the artifact risk, but on the HTML page it's still showing not a number. Yep.
Based on the output you provided, it appears that the artifact underscore risk value is nested within an object structure in your JSON response. To correctly access and display this value in your HTML, you need to adjust how you're extracting artifact underscore risk in your JavaScript function. Here's what you should do. Update the JavaScript function to correctly access the nested value. Modify your Analyze and Display EEG function to extract the artifact underscore risk correctly from the nested object structure. In this modification, the line const artifact risk equals result. Artifact underscore risk navigates through the nested structure to correctly access the numerical value of artifact underscore risk. Ensure the display artifact risk function is correct. Your function to display the artifact risk in the HTML should be like this. With these changes, your JavaScript should correctly extract the nested artifact underscore risk value from the response and update the HTML element to display the actual number instead of n, a, or nan.
Okay, this now works. Next thing, I haven't still implemented this value updating when the scroller is moved. Also, can we make sure this value is calculated over also, can we check over what window size this artifact risk value is calculated? Is it for the entire dataset or only what's viewable in the current scroller position window? Yep.
Great to hear that the artifact risk value display is working now. For updating the artifact risk value based on the scroll position, and determining the window size over which this value is calculated, here are the steps to follow. Attach scroll event listener. You need to attach an event listener to the scrolling container of the EEG chart. This listener should trigger a function that determines the currently visible data segment and then calculates the artifact risk for that segment. Determine visible data segment. The function triggered by the scroll event needs to calculate which part of the EEG data is currently visible in the scrollable area.
Okay.
Attach scroll event listener. You need to attach an event listener to the scrolling container of the EEG chart. This listener should trigger a function that determines the currently visible data segment and then calculates the artifact risk for that segment.
Okay, so we do need to check if the artifact risk, I don't know what's called risk, it's just the artifact probability. Need to make sure over which window size it's being calculated.
Determine visible data segment. The function triggered by the scroll event needs to calculate which part of the EEG data is currently visible in the scrollable area. This can be complex, as it involves mapping the scroll position to the corresponding data points in your dataset. Call Analyze and Display EEG for the visible segment. Once you have the visible data segment, call Analyze and Display EEG with this segment to update the artifact risk. The window size for artifact risk calculation depends on how you implement the function to determine the visible data segment. You have two primary options. Entire dataset. Calculate the artifact risk for the entire dataset regardless of the scroll position. This is simpler but less dynamic. Visible data only. Calculate the artifact risk only for the data currently in view or within a certain range of the scroll position. This is more dynamic and relevant, but requires a more complex implementation to map scroll position to data points. Here is a simplified outline of how you might implement the scroll event listener and the function to determine the visible data segment. Note, the implementation of the visible data segment can be quite complex, as it involves mapping pixel positions to data indices. This will require a good understanding of how your data is rendered in the scrollable area. Finally, remember to test this implementation thoroughly, as dynamically updating calculations based on scroll events can be resource-intensive and may affect performance. Consider debouncing a scroll event to limit the frequency of calculations.
Well, right, the whole idea is to, yes, calculate the artifact probability only of the data currently visible at the current scroll position. It shouldn't be complicated, should it? Yep.
Calculating the artifact probability only for the data currently visible at the current scroll position is a focused approach, but does require careful implementation. The complexity largely depends on how your EEG data is mapped to the visual representation, like a chart, and how the scroll position relates to the data points. Here's a basic outline of what you need to do. Understand data mapping. Know how each point in your EEG data array maps to the corresponding point in the visual representation. For example, if you're using a chart library, understand how data indices correlate with chart coordinates. Getting the current scroll position. Calculating which data indices correspond to the current view in the scrollable area. Extract relevant data segment. Once you know the visible range, extract this segment from your complete EEG dataset. Calculate artifact probability. Pass this data segment to your artifact risk calculation function. Assuming you have a simple linear mapping between your data and the visual representation, e.g., each data point corresponds to a pixel or a fixed set of pixels in the chart, your implementation might look like this. Key points to consider. Performance. Continuously processing data on scroll can be resource-intensive.
Why not use the sampling rate of the synthetic data and have the current scroller position as a pointer? Or is that what you were suggesting?
Using the sampling rate of the synthetic EEG data and the current scroller position as a pointer is indeed a practical and more straightforward approach. This method aligns well with your requirement to calculate the artifact probability for the portion of data currently visible in the scrollable area. Here's how you can implement this. Determine data range based on scroller position. Calculate the range of data points that are currently visible based on the scroller's position. Use the sampling rate to translate this position into corresponding data indices. Sampling rate utilization. Use the sampling rate to determine how many data points correspond to a unit of scroll length. For instance, if your sampling rate is 250 Hz, it means you have 250 data points per second. If your scroller represents 1 second per screen width, then the scroller's position can directly indicate the range of data points. Event listener for scroll. Add an event listener for the scroll action on the container of the EEG data. Calculate visible data range. On each scroll event, calculate which part of the EEG data is in view based on the current scroller position. Assuming you have a horizontal scroll and a fixed display width that represents a certain time duration. Considerations. Scroll debouncing. To avoid performance issues, debounce the scroll event. This means calculations will only occur after the user...
Can you check the backend code and tell me what the sampling rate for the synthetic EEG was? Is. Yep.
Certainly. Based on the backend code you provided earlier for generating synthetic EEG data, the sampling rate is explicitly set within the generate_synthetic_EEG function. Let's revisit the portion of your code to identify the sampling rate. In this function, fs equals 250 indicates that the sampling rate, fs, is set to 250 Hz. This means that your synthetic EEG data is generated with a sampling frequency of 250 samples per second. This sampling rate is an important parameter, as it defines how many data points are recorded per second in your EEG data. This information is crucial when mapping scroll position to data indices in the front-end implementation, as discussed in the previous message.
Okay, so can we make sure we always display, say, 10 seconds of data in the scroller, so we know exactly where we are? How to update the code to make sure this is happening? Yep.
To ensure that your scroller always displays 10 seconds of EEG data, you need to adjust both your front-end display logic and the scroll event handling. Given the sampling rate of 250 Hz, 250 samples per second, displaying 10 seconds of data means showing 2,500 samples, 250 samples per second * 10 seconds, at any given time. Here's how you can implement this. Set chart width or container size. Adjust the width of your EEG chart or its container to visually represent 10 seconds of data. This might involve setting a fixed width in pixels that correlates to 10 seconds of data. Rendering data. When rendering the EEG data on the chart, make sure that the initial load displays the first 10 seconds of data. Calculate data range for scrolling. Modify your scroll event listener to calculate the range of data points corresponding to the current scroll position. Display 10 seconds worth of data. Each time the user scrolls, determine which 10-second segment of data should be displayed based on the scroll position. Considerations. Chart scaling. Ensure your chart or display container is scaled such that 10 seconds of data, 250 points, fit into the visible area. This might require custom scaling logic depending on your charting library. Performance. Processing large amounts of data on scroll can impact performance. Consider debouncing the scroll event. Initial display. On initial load, ensure that the first 10-second segment of your EEG data is displayed. Responsive design. If your application is responsive, you might need to adjust how data points correlate to scroll positions on different screen sizes. This implementation should provide a consistent display of 10 seconds of data at any scroll position, aligning with your requirement.
Could you help me some more with implementing the necessary changes in the code? I need more specific instructions. what goes where. Yep.
Sure, I'll guide you through the necessary changes step by step. Let's break it down into two main parts: updating the front end to handle the scrolling and displaying 10 seconds of EEG data, and ensuring the back end supports this functionality. First, you need to ensure that your EEG chart or its container is appropriately sized to display 10 seconds of data. This step depends on how your chart is implemented. For instance, if you're using a library like chart.js, you'll need to configure the chart options to scale it accordingly. Next, update the JavaScript to handle the scroll event, calculating which segment of the EEG data should be displayed based on the scroll position. Here's an example of how you might modify the JavaScript. In this code, update EEG chart is a function you would need to implement to update the displayed EEG data on the chart. This function should take a segment of EEG data and redraw the chart accordingly. If your EEG data generation and processing are already set up to handle different segments of data dynamically, you might not need significant changes in your backend. However, ensure that your backend can handle requests for specific segments of the EEG data if such functionality is required. Performance. Handling scroll events can be demanding, especially if the data processing is complex.
Okay, can you actually look at the previous code and give me specific advice as to how to integrate the newly suggested changes into the existing code? Yep.
Certainly. Let's integrate the new changes into your existing front-end JavaScript code to handle the 10-second display and scroll functionality. I'll reference your previously provided code and guide you on where and how to insert the new logic. Your existing JavaScript primarily handles fetching EEG data, fetch EEG data function. Displaying EEG data on a chart, display EEG data function. Analyzing EEG data and displaying artifact risk, analyze and display EEG function. Modify fetch EEG data for initial 10-second data load. After fetching the EEG data, display the first 10 seconds of data initially. This involves slicing the data array and then calling display EEG data, JavaScript copycode async function fetch EEG data. // Existing code. Const data equals await response, JSON. If array is array, data, and then data, length. Const initial segment equals data, slice, 0, 2500, first 10 seconds of data. Display EEG data, initial segment. Analyze and display EEG, initial segment. Else. Console. Error, data received is not an array or is empty. Semicolon. Closing curly bracket. Closing curly bracket. Update scrolling logic. Add the scroll event listener to your EEG chart container. This listener will determine the visible data segment based on the scroll position and update the chart. In this code, display EEG data needs to update the chart to display the new segment. Ensure your display EEG data function is capable of updating the chart with new data. Ensure responsive design. If your EEG chart or container changes size based on the screen width, you need to adjust how the data points correspond to the scroll position. This might require recalculating total data points based on the current display size. The display EEG data function should be capable of redrawing the chart with a new segment of data. Test this implementation to ensure that the scrolling and data updating works as expected. Remember, performance is key. If you experience lag or slow responsiveness, consider optimizing the data handling or adding a debounce mechanism to the scroll event.
Do I have any event listeners at the moment? No. Doesn't matter where. $16.
Add the scroll event listener to your EEG chart container. This listener will determine the visible data segment based on the scroll position and update the chart.
Don't have an EEG chart container at the moment. We get, it's the current code we get there.
The error uncalled reference error. EEG data is not defined is occurring because the variable EEG data is not accessible within the scope of your scroll event listener. To resolve this issue, you need to ensure that EEG data is defined in a scope that is accessible by the scroll event listener. From your code, it seems that EEG data is supposed to be the array of EEG data points that you're fetching in the fetch EEG data function. To make EEG data accessible to the scroll event listener, you should declare it in a broader scope. Here's how you can modify your code. Declare EEG data outside of your functions, so it's accessible globally. With this modification, EEG data is declared globally and updated when data is fetched. This makes it accessible within your scroll event listener. Data initialization. Ensure that EEG data is initialized, e.g., as an empty array, before you try to use it in functions. Data synchronization. If there are multiple places where EEG data is used or updated, ensure that they all correctly handle this global variable to avoid inconsistencies. Performance. With global variables, especially large datasets like EEG data, be mindful of memory usage and performance implications. By defining EEG data globally and ensuring it is correctly updated in fetch EEG data, your scroll event listener should be able to access the necessary data to calculate the visible data segment and update the chart accordingly.
Yeah, this code should be elsewhere.
The error message HTTP error. Status 500 indicates a server-side issue when your front-end tries to make a post request to the analyze_eg endpoint. This typically means there's an error in the Flask backend that processes this request. Here's how you can troubleshoot and potentially resolve this issue. When this error occurs, look at the console or terminal where your Flask app is running. It should provide more details about the error. Common causes for a 500 error include issues in the request handling, errors in data processing functions, or problems in the configuration of the Flask app. Ensure that the EEG data segment you're sending from the front end is in the correct format expected by the back end. The error might occur if the data format or structure is not what the Flask endpoint is designed to handle. Add console.log statements in Analyze and display EEG to log the data being sent, to confirm its structure. Modify your analyze_eg route in Flask to include more robust error handling and logging. This can help identify what part of the backend processing is failing. Python copycode at app.root, analyze_eg, methods equals, post. Def analyze_eg_root. Try. eg_data equals request. JSON, eg_data. Hash add print statement to check data. Print, received EEG data for analysis, eg_data. Hash, existing logic. Accept exception as E. Hash log the exception. Print, error in, analyze_eg, street, E. Return JS onify, error, street, E, 500. When you get the printed data in the Flask console, check if it's what you expected. If the data is not as expected, you'll need to adjust how you prepare it in the front end. If possible, test the analyze_eg endpoint independently, for instance, using a tool like Postman. This can help determine if the issue is with the data being sent or with the backend processing itself. If the data segment being sent for analysis is very large or complex, it might be causing issues in processing. You might need to optimize the backend processing or adjust the size of the data segments being analyzed. Once you identify the root cause of the error, you can make the necessary adjustments either in the front-end data preparation or in the Flask backend processing. Remember, detailed logging both on the front end and back end can be crucial in pinpointing where the problem lies. Your Flask backend code looks well structured, and it should work for generating and analyzing EEG data. However, since you're encountering an HTTP 500 error when calling the analyze_eg endpoint, let's go through some potential issues and solutions. Ensure that the eg_data received from the post request is in the expected format and correctly parsed. The print statement you've added, print, received EEG data for analysis, eg_data, is good for this purpose. Check your console to see the output when a request is made. Preprocess_eg_data, confirm that this function handles the data correctly and doesn't throw any exceptions. Analyze_eg, verify that this function works as expected with the input it receives. The inputs, amplitude_val, frequency_val, should be within the range expected by your fuzzy logic system. The accept exception as E block in, analyze_eg is catching exceptions, but you might want to log more details about these exceptions. Consider printing the stack trace to get more context about the error, Python copycode import traceback. At app.root, analyze_eg, methods equals, post. Def analyze_eg_root. Try. Hash, existing code. Accept exception as E. Print, an error occurred, traceback, format_xe. Return JS onify, error, street, E, 500. Independently test functions, test preprocess_eg_data and analyze_eg independently, perhaps in a separate Python script or interactive session, to ensure they work as expected. Use test data, send a known set of EEG data to analyze_eg using a tool like Postman to see if it processes correctly.
Okay. Clear. Is there a problem that analyze_eg meant to have two inputs instead of one? Amplitude and frequency. But the front end is not sending it? Yep.
Yes, the discrepancy in the number of inputs expected by your analyze_eg function in the Flask backend and the data sent from the front end could indeed be a source of problems. Your Flask backend's analyze_eg function expects two separate inputs, amplitude_val and frequency_val. However, it appears that your front end is sending a single array of EEG data points. This mismatch can lead to errors, as the backend function is not receiving the data in the format it expects. Modify the front end to send required data. You need to adjust your front end JavaScript to pre-process the EEG data and extract the necessary amplitude and frequency values before sending them to the backend. To extract these values, you might use a similar approach to what is done in your preprocess_eg_data function on the backend. This preprocessing could involve normalizing the EEG data, extracting the amplitude, and computing the average frequency. To extract these values, you might use a similar approach to what is done in your preprocess_eg_data function on the backend. This preprocessing could involve normalizing the EEG data, extracting the amplitude, and computing the average frequency. Modify the backend to accept a single input. Alternatively, you can modify your Flask backend to accept the raw EEG data array as input and then perform the preprocessing on the server. This approach keeps the data processing logic on the server side, which might be preferable for consistency and ease of maintenance. In this case, your Flask route would look something like this. Data format and processing. Ensure the data format is consistent across front-end and back-end. If you're processing the data on the front end, make sure it matches what the back-end expects. Complexity. Handling data processing on the front end can increase complexity and might have performance implications, especially for larger datasets or less powerful client devices. Validation and error handling. Robust validation and error handling both on the front end and back end are crucial, particularly when dealing with complex data like EEG signals. Choose the approach that best fits your application's architecture and requirements. If you keep the processing on the back end, the front end only needs to worry about sending the raw data, simplifying its role. On the other hand, preprocessing on the front end might reduce the load on the server and allow for more immediate feedback in the UI.
Can you check the current we already seem to be doing what you just suggested. Yep. 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 Oh, come on. Not checking the code before giving suggestions.
Upon revisiting your analyze_eg_root function, it indeed appears that your backend is already set up to accept a single array of EEG data, process it, and then use the process values for the fuzzy logic analysis. The function processes the raw EEG data array to extract amplitude and frequency values, which are then used in the fuzzy logic system. Here's a recap of what your analyze_eg_root function does. In this function, eg_data is received from the post request. Preprocess_eg_data is called to process this data and extract the amplitude and average frequency. These extracted values are then passed to analyze_eg, which uses your fuzzy logic system to calculate the artifact_risk. Given this setup, the HTTP 500 error you're encountering likely stems from an issue within either the preprocess_eg_data function or the analyze_eg function. To troubleshoot further, check the console logs in your Flask application when the error occurs. Look for any printed error messages or stack traces. Ensure that the preprocess_eg_data function is correctly processing the input EEG data and that the extracted amplitude and frequency values are valid inputs for your fuzzy logic system. If possible, you might want to add additional print statements or logs within these functions to trace how the data is being processed and where exactly the error might be occurring. By carefully tracing the data flow and pinpointing where the error arises, you should be able to diagnose and resolve the issue.
Everything seems to be working correctly when loading the page. There are no errors, the data is displayed, everything is hunky-dory. However, when I scroll through the page, using the scroller, I get the following error. Yep.
The fact that you're encountering a 500 internal server error when scrolling suggests that the issue arises during the interaction between the scroll event in your front end and the analyze_eg endpoint in your back end. This error typically indicates a problem in the server-side code that's triggered when it receives a request from the front end. Let's go through a systematic approach to troubleshoot this. Front-end data on scroll. Check what data is being sent to the back end when you scroll. Use console.log in your front-end scroll event handler to log the EEG data segment being sent. Make sure this data is in the expected format and range. JavaScript copy code EEG scroll container. Add event listener, scroll, equals greater than. Existing scroll logic. Console.log, sending EEG data segment, visible data segment. Display EEG data, visible data segment. Analyze and display EEG, visible data. The log message sending EEG data segment, with length 0 indicates that the data segment being sent to the backend during the scroll event is an empty array. This is likely why the backend is throwing a 500 internal server error, as it expects a non-empty array of EEG data for analysis. To resolve this, you need to ensure that the scroll event handler correctly calculates and retrieves the appropriate segment of EEG data. Here are some steps to troubleshoot and fix this issue. Review the logic in your scroll event handler that determines the segment of EEG data to be sent. Ensure it correctly calculates the indices for slicing the EEG data array. The issue might be in how visible data start and visible data end are calculated. Add console.log statements to debug the scroll calculation. Log the values of scroll percentage, visible data start, and visible data end to see if they are being calculated as expected. Ensure that the EEG data array is properly populated with the EEG data. If EEG data length is 0, it would explain why the slice segment is empty. Verify that the array slicing logic correctly handles edge cases, like when the scroll position is at the start or end of the data. Temporarily replace the dynamic data segment calculation with a static slice of EEG data to ensure the rest of the functionality works as expected. For example, try sending a fixed segment of data regardless of the scroll position. Double-check your fetch EEG data function to make sure EEG data is being correctly populated with the fetched data. By following these steps, you should be able to pinpoint where the issue lies in the scroll event logic and correct it so that the appropriate data segment is sent to the back end for analysis. The log output indicates that your calculation for visible data start is resulting in a negative value, data start index, -1232.
What? Why?
Since array indices in JavaScript cannot be negative, this leads to the empty array being sent for analysis. To fix this issue, you need to adjust the calculation of visible data start and visible data end in the scroll event handler. The objective is to ensure that these indices are always within the bounds of the EEG data array. Ensure non-negative start index. Modify the calculation of visible data start to ensure it's never negative. One way to do this is to use math.max to set a lower bound of 0. Handle end index properly. Adjust the calculation of visible data end to ensure it doesn't exceed the length of the EEG data array. Here is the updated scroll event listener with corrected index calculations. Initial data population. Make sure that EEG data is correctly populated with the EEG data before the scroll event is triggered. If EEG data is not populated or is shorter than expected, this can also affect the calculation. After making these adjustments, your scroll event should correctly calculate the segment of EEG data based on the current scroll position and send a non-empty array for analysis. This should resolve the issue of the 500 internal server error occurring due to empty data being sent to the back end.
Yeah, the start index and end index being 0.
The logs indicate that both visible data
cool.
start and visible data end are being calculated as 0, which results in an empty array being sent for analysis. This suggests an issue with how the indices are being calculated based on the scroll percentage. Let's troubleshoot and correct this. Scroll percentage represents the relative scroll position. Visible data start should be the index in EEG data where the visible segment starts, based on the scroll position. Visible data end should be the index where this segment ends. Review total data points. Ensure total data points is correctly set to the number of data points you wish to display at a time, 2500 for 10 seconds at 250 Hz. Adjust calculation formula. The formula to calculate visible data start and visible data end should correctly map the scroll percentage to the indices in EEG data. Given your current setup, here's a revised approach. Ensure that EEG data is correctly populated and its length is as expected. Max start index is calculated to be the highest possible starting index for the visible data segment. This ensures that when you're at the end of the scroll, you don't try to access beyond the array's length. Visible data start is calculated based on the scroll percentage and this maximum start index, and it's bounded to be at least 0.
Yes, same problem.
The log output indicating that both data start index and data end index are 0, despite a non-zero scroll percentage, suggests that the calculation for the start and end indices is not reflecting the actual scroll position correctly. Let's refine the logic to correctly map the scroll percentage to the indices in the EEG data array. Ensure total data points is correct. Confirm that total data points reflects the number of data points you want to display, 2500 for 10 seconds at 250 Hz. The calculation of visible data start should be based on the scroll percentage of the total possible scrollable length. This length is EEG data, length, total data points. Visible data end should be calculated as visible data start plus total data points, but ensure it does not exceed the length of EEG data. Here's the updated code. Data initialization. Make sure that EEG data is correctly initialized and populated with the EEG data before the scroll event is triggered. If EEG data length is less than total data points, this could affect the calculations. By applying these adjustments, the script should correctly calculate the start and end indices for the data segment based on the scroll position.
Okay. So scroll percentage seem to be working okay. The data start index and data end index are still always 0. But the chart is displaying correctly when scrolling. The artifact risk value is always the same at 0.89. Yep.
Given your description, there are a few separate issues to address. Data start and end indices always 0, S. Since the chart is displaying correctly when scrolling, it suggests the data segment calculation might actually be working, but the logging of start and end indices is not reflecting this. This could be a logging issue or a discrepancy in how data is being passed or processed. If the artifact risk value is always the same, 0.89 in your case, it might indicate that either the same data segment is being analyzed repeatedly, or the analysis function is not sensitive to the changes in the data. To check this, log the data being sent to the analyze_EEG endpoint. If the data changes as expected when scrolling, then the issue might lie in the analysis function's sensitivity or logic. Verify data segment length. Check if the length of visible data segment changes as you scroll. If it does, the issue is likely not with data segmentation. Log data sent for analysis. In Analyze and Display EEG, add a log statement to print the data being sent for analysis. Backend function check. Ensure that your analyze_EEG function in the Flask backend is processing the input data correctly and is sensitive to changes in the input data. Consistency in data processing. Confirm that the pre-processing, like normalization or feature extraction, applied to the data before analysis is consistent and appropriate for the type of analysis being performed. By conducting these checks, you should be able to pinpoint where the issue lies, whether it's in the data segmentation, the data sent to the backend, or in the analysis logic itself.
I'll see you next time. Don't forget to check the Bionichaos website.